After updating my Ben Eater SAP1 breadboard CPU to use a full 16-bit memory space, my next goal was to upgrade it from using 4-bit instructions to 8-bit instructions. However, as I developed my design for implementing 8-bit instructions, I realized a number of shortcomings of both my 16-bit memory design and my extended control lines project from a few videos back. Learning from those mistakes, I then played my design forward to figure out key things I should do now to enable modules and design elements I intend to design later. So I ended up doing a significant redesign of much of my breadboard TTL computer. At this point, very little of the original Eater SAP1 remains. In this video, I'll go over all those design changes and then talk about what comes next for my breadboard TTL CPU computer. So getting to this point in the project took much longer than I anticipated. For sure, part of the reason is I do this in my spare time, so I don't have all the time to kind of motor through it. But there's a lot of issues, a lot of challenges I had to overcome, more so than I originally anticipated when I started off. One of the main challenges I had to overcome is that I'm starting to push the boundaries of stability for the size of the breadboards that I'm using. I started to experience issues from the inductance and the capacitance of the breadboards and the fact that I'm running longer and longer wires to get to modules that are further and further apart. I'll be going into the details of those issues later, so I'll just say that for now. There was also unanticipated complications when I came up with the design of the 8-bit instructions. My first step was actually to design the instruction set that I was going to use. And I wanted to design the instruction set not of the computer I was going to build today, but the computer I wanted to build tomorrow, so to speak. As you recall, my goal here is to build up this TTL breadboard CPU so that I can calculate 64-bit math such that I can actually do the factorial for a 64-bit number. And there's a lot of things I need to add, notably a stack pointer so that I can do stack operations like pop and push and doing calling of subroutines. When I kind of planned all that out, one of the things I realized was a lot of the elements of my original design for the expanded control lines for the 16-bit memory that I just did in my last video was not quite right, or not quite what I needed. And so I needed to change a lot of the stuff that I already implemented so that I could build the infrastructure and the design such that I can build the things that I need to build next, rather than having to completely redo everything with every project. So I kind of bit the bullet and redid a lot of things in this project, a lot of things that I previously done, and also redid some more of the original Eater SAP1 and making this a completely new computer at this point. One of the significant changes I made was adding something called memory mapped I/O. I realized that it would be an important step, especially around how I would add a display that could display 64-bit numbers and control other aspects of the computer. One of the things that I realized was not going to work out well was my original control lines architecture. I needed more control lines, and the original design would have me put another EEPROM in with another 238 in so that I could have another, I believe the number was another 12 lines. However, that would have been pretty unwieldy. There was a lot of wires going on. The design just wasn't really expandable. So I had to rethink my control logic. That in combination with my memory map controller now allows me to control a lot more things, but do so in a much more elegant manner than what I previously implemented. The next thing I realized was that for the instruction set that I was looking to implement, my compiler that I had implemented previously, the project that I called BespokeASM, linked down in the description, it had to change. It had to change rather significantly. So I almost completely rewrote that assembler so that I could accommodate the various instruction types, the operand concepts that I had to implement in this project. I'll be going over those details a little bit later in the video. I also realized that 8-bit instructions didn't quite have enough space in it to have all the instructions that I wanted to implement. So I ended up implementing a concept called extended instructions. If you ever program the C80 CPU, you know what I'm talking about. Basically, it's a special instruction that turns a 1-byte instruction into a 2-byte instruction, thus allowing multiple variations on the kind of opcodes that you can actually pass to the microcode. And after doing all that, I also realized that I didn't have enough address lines going into the EPROMs of the control logic, and thus I had to find a completely new EPROM other than the 28C256 that I had been using that would allow me to give it more control signals to be able to have finer control over the microcode that then executes every step. So all of that just added up to me completely redoing the control lines and the microcode of this computer. Finally, as I already kind of indicated, when I got everything together and I verified all my wires were right and that all the things were connected together as I designed, it just didn't work. And I was quite frustrated with that, honestly. It took me a while to debug it, but as I indicated earlier, the size of this breadboard computer is starting to create problems, notably around the inductance of the wires and the capacitance of the boards and such. And so I had to figure out how to address that so that this computer could still work. The good news is I did. And as you saw in the opening sequence, the computer is working and it's working just fine. But it took me a while to figure that out. Admittedly, I'm not an electrical engineer, right? So there was a lot of learning I had to do in order to figure out why certain things I saw happening were happening. So I spent a lot of time to sort that out. And I'll describe what happened and how I addressed that. But before we get into the design of this computer, I want to discuss the name of this computer. After I published my last video, someone on Reddit asked me what is the name of the CPU. Of course, I can't call it the Ben Eater SAP1 anymore because it's very much not that. And admittedly, I didn't have a name. When the person asked, I never had thought about it. So, I couldn't think of one myself, so I did what any normal person would do. I asked my teenage daughters, what should I name my breadboard CPU? After about 100 milliseconds of deep contemplation, my oldest daughter blurted out, call it PUTEY Compute Face. So, there you go. That's the name. Admittedly, I'm not going to call it PUTEY Compute Face. I shortened it down to PUTEY, or more specifically PUTEY-1, because I'm also already thinking about a second version of this computer that I will call the PUTEY-2. But for now, this is the PUTEY-1. But since I have more work to do on this is the PUTEY-1 Beta 1. So that's the name of the computer. From now on, I'll be referring to it as the PUTEY-1. Okay, let's get into the design here. Let's go over the goals of this project. Admittedly, the goals are pretty straightforward. First and foremost, I want to enable 8-bit instructions. Or more generally, I want to enable a richer instruction set than what would the original SAP1 afforded with 4-bit instructions. The 4-bit instructions only really allowed 16 instructions to be defined. 8-bit instructions theoretically would allow 256 instructions to be designed. What you'll see later when I actually get into what I ended up implementing, I actually implemented 9-bit instructions that enables 252 instructions to be defined. The second goal is to rework the general architecture to enable some future projects. The future projects that I have in mind include enabling a stack pointer, I/O such as a display and a keypad, and a more capable ALU. As I thought forward as to what I would need to implement in order to enable a stack pointer or a display, I realized that the path that I was on with my original design, as documented in my last few videos, was insufficient, and I needed to enable some new points of architecture, most notably a memory map controller. I'll be getting into the details of how to do that later, but for now, just know a lot of the designs that I originally came up with have been altered to be able to better enable the future architecture that I wish to implement. I realized the first thing I needed to do before I designed any hardware was to design the instruction set I wanted to enable. Doing this would then tell me what hardware I needed in order to support it. The instruction set I came up with was inspired by my experience programming and assembly on the Z80 CPU. The basic idea is that there would be instructions and operands. The core example is the move instruction. Note that it has an operation, the move, and operands, the A, I in this example. The operands are ordered such that the first operand indicates what is receiving the data, and the second one indicates where the data is coming from. So what this instruction on the screen represents is that we're going to move or really copy the value currently in register I and place it into register A. Now what will this instruction look like in machine code? Here you have the machine code designated for this instruction. The way I came up with things is that certain bits will indicate the operation and other bits will indicate the operand. Here, the first two bits, the 1 and the 0, indicate the operation is the move instruction. The following 6 bits indicate the 2 operands, each indicated by 3 bits in order. This allows instruction parameterization to be indicated in the machine code. If we switch the operands around in the instruction, that is, move the A register into the I register, the corresponding bits in the instruction will get swapped. Here, we turn the instruction into move the value in register A into register I by switching the order of the operand bits. Note that for the CPU, it doesn't matter what the bits are for any given instruction. This interpreted meaning to the bits is for human convenience, and it does make implementing an assembler to support these instructions a bit easier. I'll be getting into that later. Now let's look at another example. In this case, we're going to move the value of hex 20 into register A. Note that the instruction again has 2 operands. However, this time, the second operand is a different type. It is called an immediate value. Basically what it's saying is that the value to move into register A is a specific value that is identified by the byte that following the instruction. Here you see the bits for the hex 20 following the instruction bits. This brings us to the concept of operand types. For the move instruction, the operands will indicate where an 8-bit value is coming from or where that 8-bit value is going to. So we have 2 operand types, an 8-bit source and an 8-bit destination. For the CPU I've built so far, here you have all the possible 8-bit sources and destination. You'll see there are some registers, the A, I, and J registers. There's the memory address register, actually more specifically the value at the memory address that the memory address register is pointing to. There's also the immediate value, which is what we just discussed in the prior example for the move command. For the 8-bit destinations, you have a similar set, but the immediate value is missing because you simply cannot move a value into the byte that follows an instruction in ROM. For other instructions in the instruction set I've developed, I have other types of operations. Values that are incrementable, 16-bit sources and destinations, and a memory address, which is a special kind of a 16-bit source. One thing you will note about all of these operand types is that there are different kinds of operand values in each of the types. I just demonstrated this with 2 instances of the move command. In one instance, the operands were both registers. In the other instance, one of the operand was an explicitly provided value. Looking at the list of possible operand values for the 8-bit source, you see registers, values in memory, and explicitly provided values. This brings us to the topic of addressing modes. Loosely speaking, an addressing mode is a method for accessing data by the CPU. On my CPU at this time, there are 4 types of addressing modes supported. The first is an immediate value. This is a value that is provided directly in the machine code, typically immediately after the instruction that makes use of it. Hence the name immediate. The second type is an indirect value. This is a value that is located at a memory address that is provided in the machine code. You could say that the memory address is an immediate value, but the value that we are interested in is at the location in the memory pointed to by the memory address. So we say this addressing mode indirectly refers to the value. The third type of addressing mode is the register. This is simply saying that the value is located at one of the hardware registers in this TTL CPU. Examples include the A or I or even the J register. The fourth addressing mode is the register indirect. This addressing mode indicates that the value is at a memory address that is currently contained in the register. This is similar to the indirect value, but rather than the address being itself an immediate value, the address is now in a register. Right now, the only register on my CPU that supports this is the memory address register, or MAR. I do plan on adding 16-bit registers in the future that can support this sort of addressing mode, but they're not there yet. So with the operands thoroughly explored, I can give examples of the other instructions. Let's consider the subtract instruction. The subtract operation subtracts a value of the operand from the value in register A and places the results in register A. Here, we are subtracting the immediate value of hex 20 from the value in register A, then placing the results in register A. Note that the operation bits are longer than the 2 bits that we used previously in the move command. This instruction has one operand, which is an 8-bit source type operand. The 8-bit source operand requires 3 bits to indicate it, thus the remaining 5 bits can be used to indicate what the specific instruction is. In this case, the second operand is an immediate value, so the machine code for this instruction is immediately followed by a byte that indicates the value to be subtracted. We could go through all the instructions for But for simplicity, I made this table that describes all the instructions that the current version of my TTL CPU supports. Here you have control instructions like halt and jump and conditional jump. I will point out that I also made a jump if equals instructions that jumps to the address indicated in the first operand if the value in the second operand is equal to the value that's currently in A. There's also the move and various arithmetic operations. Note that for each operations, I indicate the bit prefix and then what operand types are used as a parameter in the instruction bits. I've also created this concept called extended instruction. This is a concept that plainly I borrowed from the Z80 instruction set. What it does is allows me to go beyond the 256 instructions that a pure 8-bit instruction set would allow, and instead be able to get more, in this case 512 instructions. The way an extended instruction works is that the first byte of the instruction is actually a special instruction that simply sets a flag and then loads the next byte into the instruction register. The flag indicates that the second byte should be interpreted as an extended instruction rather than a normal instruction. The second byte could have been the same bits as a normal instruction, but now means something completely different in the microcode. Here's an example of an extended instruction that I defined. What it is a swap command, where it swaps the values in the two operands. And here in this example, I'm swapping the values between the I and J registers. Note that the first byte of the machine code is hex FF. This indicates to the microcode to set the extended flag and then load the next byte into the instruction register. The second byte now looks like a normal instruction, but it will be interpreted differently because the extended flag is set, thus doing something different in the microcode. Okay, so that's the instruction set that I designed for the CPU. If you look closely, you'll notice that the bit prefixes for each instruction don't comprehensively cover all the possible values that you'd get in the full 8-bit range. I did this to allow for room for future instructions I wish to implement as I build on this TTL CPU, most notably like pop and push for a stack operation. Now that we understand the instruction set and how I went about designing it, let's take a look at the hardware design to support this instruction set. The first hardware design change to look at is the instruction register. As you look at this design, you'll see that my instruction register design actually has the instruction register, the step counter, and the reset logic all built in the same design. So I'll go over all those real quick. The first thing you'll note is that the instruction register itself right here is pretty much the same design as the original Ben Eater SAP1 instruction register, except instead of having one 74 LS 173, it now has two in order to count the full 8 bits. I also added one of the 74 LS74 flip-flops in order to control the extended flag. This extended flag is controlled by this extended control line, XTD control line, which when at high will allow the clock signal to come through this AND gate right here, and thus enable the flip-flop to be on. And then the extended control instruction address line will come out here. The step counter I'm using is basically the same as my last design when I updated the step counter. It is a 3-bit step counter allowing up to 8 steps in any given instruction, and then automatically resets itself when it reaches the 9th step. One other change that I made was adding this RC circuit right here in order to try to attempt to do a power on reset type circuit. What it does is when the power is off, everything's at ground, and when the power turns on, this capacitor will allow the 5 volts to come through, and thus a high signal will go into this OR, which will then essentially cause this reset circuitry to pass the CLR signal to the rest of the computer. In practice, I've found that this works maybe 80% of the time. I haven't really debugged it as to why it doesn't work 100% of the time, but for the most part, it works well enough for me and my purposes, so I'm happy with it. The final thing I'll point out is that at the bottom of the schematic, I have all the various address lines coming out of this instruction register. These are the address lines that will go down to the control logic and control the EPROMs that are controlling the microcode. So indicate what step we're on, what the instruction to be used is, and whether the extended flag is set or not. The next change in my hardware design was actually to the control logic itself. And for the control logic, you can see now that the design is much simpler than my original design. Now, I do have 48 total control lines that I can use for my microcode and the computer in general. I've been able to put this down to 2 individual EPROMs and then a set of 74 HCT238 demultiplexers. What enabled me to do this was essentially finding this EPROM right here. This EPROM, the 27C4096, is a 16 megabit EPROM where the values are actually arranged into 16 byte words. And so the address lines, if you look at the actual pinout for this thing, it ends up having a total of 18 address lines from A0 to A17 and 16 data lines from O0 to O15. It ended up being a very concise way to add more address lines and control lines to my control logic. I did have to update my microcode generation to be able to generate microcode for this type of EPROM as opposed to 28C256, which I have used previously, but that wasn't too hard to do. And you can see the updated code in my GitHub repository, which I link below. One of the things I will note is that this EPROM is not electrically erasable. One of the convenient things with the 28C256 that I previously used is that it would be erased when I uploaded new data to it. However, now you see this little window here. In order to erase it, to put new microcode on it or change the microcode in a way, I actually have to put this under UV light and kind of bake it under UV light for about 15 minutes. Not hard to do, a little bit inconvenient, but given that I'm not changing the microcode all that often, it works. So that's just the one note that I would make. You would actually have to get an EPROM eraser to be able to use this kind of EPROM. The final change that I want to highlight here is adding the memory map controller. Now, the memory map controller, the way I implemented it, it is a fairly simple logic design. But before I go into the design, let's actually cover what it is actually going to do. Here you see the original memory map of my TTL CPU as it was at the end of my last video. Basically, I have 32K of ROM from addresses 000 to 7FFF, and then I have 32K of RAM from address 8000 to FFFFF. So that works great. Now, in order to add memory map I/O, I have to take a section of this memory space and dedicate it to being used for the memory map I/O. So what I ended up using for my new memory map is what you see here, where I took the addresses from 7800 to 7FFF and dedicated them to the memory map I/O. This does remove 2K of usable space from the ROM, but, I had to do it somewhere, and I decided to do it over the ROM rather than over the RAM. If I end up realizing that I actually needed that 2K for ROM space, I'll go ahead and change it such that the memory map is somewhere else. But for now, this ends up working pretty well. And getting back to the design, what you see here then is the logic design to implement that memory map. The first thing I'll point out is this 4 input AND gate. And what it's looking for is that address lines A14 through A11, when they're all high, it will go high, indicating that we are potentially in the memory map space. If you look at what hex 7800 looks like at the bit level, you'll note that these 4 bits will always be on in that entire address range. The next thing I'll look for is that address line 15, whether it's high or low. If address line 15 is high, then I know I'm actually dealing with a RAM address, and then it enables the RAM enable line here, which then turns on the RAM module onto my device. If this address line is low, then I know that I'm either in the ROM space or the memory map space. To determine whether I'm in the ROM space or memory map space, I do combine the signal with what's coming out of this 4 input AND and determine whether it's the memory map space that should be active or it should be the ROM that should be active. And the actual control line that's coming out of here for ROM is actually active low. This works because my ROM chip, its chip enable is active low, so this works well for that chip. If the memory map enable is high, then I activate these 74 HCT238s. And what these do is look at the lower address lines to then determine which of the individual memory map lines should be active. The way I set it up is that I end up having 8 memory map lines that represent 16 bytes of address space. The lowest, memory map 0, this is at address 78000, and it's active when at any memory address from 78000 to 780F. This next one would be active from 7810 to 781F, and so on and so on, until we get to addresses at this regime, which now I'm activating for 128 byte ranges. Here I have 7 rather than 8 because one of the control lines coming out of this multiplexer is actually used to enable this multiplexer up here, which controls the 16-bit lines. At the top of it all, I've actually also implemented a 1K byte memory map to be used for something. This could possibly be used for a very large display or something like that. Admittedly, I don't know what I'm going to use these all for yet. I try to create a general design that would seem to be useful for most of the scenarios that I can imagine. So I have a few 16-byte maps, 128-byte maps, and a 1K byte map. I figure for what I'm going to be doing with this TTL CPU, that's more than sufficient. You'll also note this mysterious A16 address line that I have over here on the left. Now, the thought behind that is my RAM chip that I'm using in my design is actually a 64K RAM chip. And if I'm able to use it, that would be great if I could figure out how to use it. I haven't quite figured it out yet, but I did realize to be able to use it, I need another address line, and that needs to fit into my overall design. So I enabled my memory map controller to take this address line into account. So the RAM is going to be active when the address line 16 is low and address line 15 is high, or address line 16 is high and address line 15 is low. So that would be the complete range where the RAM is active. However, I am not using anything in the upper 32K bytes of the RAM yet. And so for now, this address line is actually tied low and it doesn't change at all. A future project I may figure out how to use this in a future project. What I am thinking is that my stack pointer will point into memory in this upper 32 bytes of my RAM chip, thus having my stack not collide with any of the RAM that my programs use. The other changes were to my RAM and ROM module. If you look at the RAM module design, if you look closely, you'll realize this is for the most part the same design as I had for my last video. The only obvious change is that the ROM is not connected, and so this internal data bus within the RAM module is only impacted by the RAM itself. Otherwise, everything else is mostly the same. I was able to figure out a more elegant way to do this activation logic, so that is a small change. And now I do have this memory device out and memory device in logic that needs to be combined with a RAM enable signal before it activates or the RAM out or the RAM in. But this is part of the new memory map design that I enabled. Similarly, the ROM module, pretty much the same thing as the last time, but the only major change is, other than the fact it's not connected to the RAM module anymore, is again, the ROM enable line is combined with memory device out control signal to actually activate the output from the ROM chip itself onto the data bus. If this memory device out is not high, then nothing will be written to the actual address bus. The final change it's a subtle one. It actually has to do with the run mode selector. This is where the address dip switches are combined with the actual address lines coming up from the program counter and memory address register. And based on the run mode, we either select the dip switches or the address lines as to what goes into the memory devices. The only change here is actually right here, where this mysterious address line A16 that I talked about previously, where it's tied low. So effectively this address line is unused because it's always at 0. But that's the only real change here on this module. Building this update was pretty straightforward, but it did require me to almost completely take apart the entire previous version. To do that, I first marked each control line with a little flag that I printed out so that I could more easily find where each control line goes when I put things back together. I also found it easier to simply remove all prior control lines because my control logic change changed all wire lengths anyways. I did get a chance to reuse many of my prior yellow wires, so I didn't end up wasting them. It's just I had to cut new lengths for all the new positions. There's also many opportunities to consolidate logic gates. Many of the modules, new and old, use only a few of the gates on each logic chip. The consolidation opportunities were limited by my layout, but I was able to reduce the chip count over my schematic design. I also created some custom inline LED bar graph modules. As you'll note from my layout here, I like using the bar graphs because I find them to be much more aesthetic and much more explanatory than the round discrete LEDs. However, these kind of bar graph modules, you can see they take up a lot of room on a breadboard because you have to have connections on both sides of the center line. So I created these sort of modules that I use. Pull one out here. Yeah. So I created these modules, and what these modules are is it's an LED bar graph. However, rather than it being a dual inline like these modules, this is a single inline set of pins. And so my layout options on the breadboard are much greater. I can have them sit off to the side like I do here, rather than having them occupy both sides of the breadboard line. Now, to make these, all I did was I designed a custom PCB, and it uses square LEDs or actually rectangular LEDs. Plus, I have some resistor networks that act as the current limiting resistors for this. There's one pin for each LED, plus one more pin for the common ground. And so all I need to do is just put it in place, have a ground line that goes to right here where it says ground, and I have an LED module. And it looks like I pulled out one of these wires too. I'll have to fix that later. One of the other advantages of building these LED modules is that you can use a custom color arrangement. Here is a 16p LED module for my instruction register. And you can see I use different colors, and each of the colors represent a different part of the activation lines for the instruction register, where these green ones are the step counter, the blue ones are actually the instruction register value, the red one is the extended bit being active, and the yellow ones are control flags. Admittedly, right now I only have 2 control flags in use, the 0 and the carry. The other 2 control flags are there for future expansion. I also made these 8 LED modules for areas on the board where have only 8 bits that I'm trying to highlight. For example, most of the registers only have 8 bits, and so I may over time transition them from these bar graph modules to these custom made LED bar graphs. The KiCad projects for these LED bar graphs that I made are available in my GitHub repository. The link will be down in the video description. I also want to point out a change that I made for which I didn't publish a schematic, converting the display register to a memory mapped I/O device. This change takes the control line from the memory map controller here to the display register, rather than taking a control line from the control logic down here. I also had to AND the memory map control line that I'm using with the memory device in control line, so that the output register would, when both of these are high, would read the data on the data bus and read it into the output register so that it would be displayed on my display there. This demonstrates the convenience of the memory map I/O. I don't need control logic dedicated to it, nor do I need a special instruction for outputting the display. I can use the existing move command and a specific address, and I get the same result. As I indicated, I use the first control line in my memory map controller that responds to memory address 7800 to hex 780F. To set the display register to a value, I just have to move or copy a value to that memory address. For example, to set the display register to the immediate value of 21, the assembly instruction I would use is move square brackets at address 7800, comma 21. As I indicated earlier, I had to completely rewrite my BespokeASM assembler in order to enable the new addressing modes of this version of the breadboard TTL CPU. Now, I'm not going to go over all of the changes to the assembler, as you can read about them at the BespokeASM GitHub repositories wiki page, which you can find right here. However, let me show you how an assembly program would look like for this version of the computer. The first thing I want to show you is actually the BespokeASM configuration for this version of the computer. Like before, you have a general configuration that tells you a little bit of the details of how the overall computer works. The address size is 16 bits. The computer stores multi-byte values as little endian. And the registers that are available to the computer right now are A, I, J in the memory address register. In this configuration, you also need to configure the various operand types that I discussed earlier. Here I have operand types set up as the 8-bit sources and destinations, 16-bit sources and destinations, address sources, and incremental destination. I can show you operand sets, how they're configured. Basically, it's just a list of various instances of operands that fit this general operand type. So the 8-bit source operand type consists of the A register, I register, J register, and indirect value plus an immediate value. Then we have to configure each individual command such that the assembler knows what machine code to emit for that command. And to do that, basically you have to tell the assembler what is the bit prefix for that individual command, and then what operands are allowed to be used. Here I configured the move command to have a bit prefix value of 2 that has a size of 2 bits, and then it has 2 operands coming from the 8-bit destination and 8-bit source. The thing I'll also point out is that I can tell the assembler that there are certain operand pairs that are just not allowed. Specifically, moving the A register into the A register is a nonsensical type of activity, so we don't allow it. And in fact, while you could probably do something that is literally moving the A register into itself, it has no effective value within the computer. And so what I end up doing is using that specific opcode that the bits of this prefix plus the bits of each of these operands represent. I use that opcode for another command elsewhere. So that's how you configure BespokeASM so that it can compile the machine code for this particular CPU. Here I'll show you how this is going to look for a particular program. And to do that, I'm going to use a fairly straightforward program calculating the Fibonacci series. What this program is doing is calculating Fibonacci until the value overflows and this ends up becoming too large for the 8-bit register in which we're calculating it. To do that, the first thing I do is set a constant for the output. The compiler will use this to represent this actual address here. This is the memory mapped address that controls the display register, as I discussed previously. And then the code here, this is fairly straightforward code for calculating the Fibonacci sequence. I start off by setting the origin of the code to address 0, meaning I'm writing code that will actually end up being placed in the ROM address space of my computer. The first thing I do is I initialize the display register to a value of 1. You can see what I'm doing here is moving the immediate value of 1 into the memory location described by the output constant, which is 7800. Because that memory location is a memory mapped device, what ends up happening is that value of 1 gets placed into the display register rather than RAM or ROM. The next thing to do is actually initialize both the I and J and A registers with a value of 1, and then I just start the Fibonacci loop, which is adding the J register to A. If it carries, then I jump back to start and restart the loop all over again. If it doesn't carry, I move the A value into the display register so that it can be displayed on my device. I move the I register into J and then A into I. This is the part of the Fibonacci sequence where you take the previous 2 Fibonacci values, and then I jump to the start of the loop and start the sequence over again. Okay, let's go ahead and compile this program and see what we get. So to do that, here is the interface for BespokeASM to kind of give you a sense of all the various options. What we are going to do is simply call BespokeASM compile. Now, since I'm going to want to generate a binary image for the ROM file, I do want to set the end size or end address for the binary image to be 32767. That is basically 32K, and that's what this is telling BespokeASM to generate a binary image that has addresses from 0 to 32767 in it. What BespokeASM will do if the code that you're compiling doesn't fully fill that binary image, it will pad the binary image with zeros, and that is actually set by the binary fill option. I'm not going to specify it because the default value is 0. I'm going to want to pretty print this so that we can inspect the results as human beings rather than looking at the binary code directly. The config file that I'm using that controls the actual assembly language is here in the repository that I have, and it's what I just previously showed you, which is this one right here. Then I give it the actual assembly file that I want to compile, which is the Fibonacci series, and then we compile it. There, the pretty print output tells you exactly what it compiled to. It gives you the bytecode that it's generating and also the binary code if by chance you want to manually enter it, which we can't since it's actually set in the ROM space. But you could compile this such that you tell it that the addresses to compile it against are actually in a RAM space, and then you can hand enter the program yourself. But we're not doing that today. We're creating a binary image. And if we look at the files, you can see the binary image right there. If we want to inspect the actual binary image, let's go ahead and look at that and see what we get there. And you can see it is mostly zeros, and the entire program is composed in a subset of the first line of bytes. Okay, so that's the assembly language for this version of the computer. The other thing I wanted to show real quick is just the microcode that we had to generate. So the microcode in my setup is configured by this configuration file, and this configuration file is run through a program that I wrote in Python that uses this to figure out what the exact binary images should be that will get burned into the EPROMs of the control logic. I'm not going to go over this line by line, but the thing I will point out is that I had to change the program that I used for generating the microcode image for the primary reason that I have different EPROMs in this setup as what I previously had, and also basically a different arrangement of control lines. So the program is updated. I now have a v2 to it, and you can find that in my repository. In order to run it, what we end up having to do is just simply, let's go to the microcode directory. You can see the actual configuration file there, and we will run the Python 3 program that is found at my microcode generator v2, and it is the generate microcode.py file. If we run it without any argument, it will tell you that you need a YAML configuration file, and that is the YAML configuration file that I just showed you that is actually right here. So let's go ahead and run it, and we will generate the microcode. And you see, rather quickly, it generates microcode, and then it generates a file, a binary file, which you'll use to burn the EPROMs in the control logic. We can take a quick look at the actual images, see what we see here, and that is the microcode. Okay, let's go ahead and burn the Fibonacci program that we just compiled onto the system ROM for my computer, and then try things out. Let's get it running. So here I pull out the ROM and put it in the burner here. Then I burn it. And here I'm loading the binary image that we just generated, that we had BespokeASM generate for the Fibonacci program that we just compiled. There, it's done burning. Let's go ahead and put the ROM back in place. Get the computer out of the way, and let's try this out. Okay, let's turn on the power. You see the power on reset kind of hold things for a moment. And in this case, this is an example where it didn't reset completely properly. And so I'm just going to go ahead and manually reset the computer. And here goes the Fibonacci series. You see the display being outputted. You'll notice that each time the display is updated, you see my status LED for the memory map control line also flash. So those are the moments that we're actually writing a value to the memory address, which represents the display register. So there you have it. My PUTEY-1 breadboard TTL CPU has been significantly revised with a more robust control logic, a memory map controller, and an 8-bit instruction with extended instruction bit. I'm pretty happy with this design, and I'm eager to build out the rest of the needed improvements to get to my goal of calculating 64-bit math on this TTL CPU. Thank you for watching. I hope you found this video to be informative for your own TTL CPU project. If you enjoyed this video, please be sure to like this video and subscribe to my channel. If you're working on your own TTL CPU project, I would love to hear about it. So do please leave a comment down below. As always, all the schematics, software, and documentation relevant to everything I talked about in this video is available in my GitHub repository, which is linked in this video's description. My next video is going to be focused on adding a stack register to this computer, so stay tuned. That will probably come out maybe in a month or so. As I always say, I don't do this full time. This is a part-time hobby, so it takes me a while to get each video out. Until next time, goodbye and enjoy your TTL CPU project.